Hello, class. This is our first lecture. There will probably be a lecture 0 and a lecture 0.5 that I put up to where I discuss the syllabus and the individual, like lecture topics that we're going to be working through over the course of the semester. I haven't put all of that together yet, but I wanted to get the first couple lectures of the course down. So this is the first lecture of the course. This lecture is going to be on dimensions and units. All right. Dimensions and units, it's really the first lecture that I like to do with all classes that I've had for the first time. One cohort of students, I should say, that I've had for the first time. I may have you again. I don't know, I've taught 34 different subjects in 4 different programs, so actually probably a lot more than that. But the one thing that's most important to any engineer, irrespective of whether you're taking network theory, engineering mechanics, electromagnetic field theory, and whatever field that you go into, dimensions and units, and understanding what the primary dimensions are, how those primary dimensions then can be used to derive other dimensions and units for those other dimensions based on those primary dimensions, so that we understand how various different dimensions, and by dimensions I mean area, force, energy, power, those are dimensions. But the units for those dimensions are watts, joules, newtons, as you see them. And as you've probably been taught them up to this point. That is not how professional engineers view and understand dimensions and units. And that's what I want to clarify, and that's what I love to clarify, because it's such an eye-opening experience for any students to really then understand the power of understanding dimensions and the units for those dimensions, and how those units then interplay with other dimensions in equations as variables and give us that. So that dimensional homogeneity is one thing. We're going to talk about that today. But then this also extends into your experimentation later on. Because if you use dimensional analysis and similitude, extensions of a real understanding of dimensions, that then helps you decrease the amount of experiments that you would have to find various relationships between various different variables in engineering equations. And I'll give you a good example of this. The Reynolds number, which is a dimensionless number for fluid flow analogies. That's a number. Coefficient of lift, coefficient of drag. There's a lot of things. So we won't really look at dimensional analysis and similitude. That will be an extension that you could go into, and but what we are going to look at today is we're going to look at dimensions, how dimensions interact with one another. I think that's pretty much what today's lecture is going to be about. But why is it so important? 85% of all engineering mistakes, and a lot of those mistakes could end up in fatalities. A lot of those mistakes, for instance, the Mars orbiter. a $600 million satellite that was supposed to go around Mars. When it got to Mars, got all the way there, everything worked out fine. But since it was a collaboration with the European Space Agency, we were using miles above Mars as the height for the orbit, for the Mars orbiter. And the European Space Agency that we were working with was using kilometers. And so instead of 110 miles above the Martian surface, it was 110 kilometers. And of course, that was inside the atmosphere, and the Mars orbiter burned up, and we lost all of that money and development and everything else. And all that knowledge, that potential knowledge we could have had. Why? Because of miscalculation in units. The Hubble Space Telescope is another good example of that, where the difference between precision and accuracy, we had the finest polished mirror in the world, but unfortunately it was a centimeter off. So, things like that. You have to be very cognizant of your dimensions and units. Those are the things that are going to cause things to go wrong. So let's start first. What are the primary units? Now, usually when I'm teaching this in an in-person class, I would, call on people, hey, anybody know what the primary units are? But obviously I can't do that here. And but the reason that I want to do this asynchronously is to get the information out there and let you guys learn as much as you possibly can as compared to being in an in-person class without the coronavirus. All right, so let's go through this. When we look at the primary units, I should say, and dimensions, right? Because we want to know what those dimensions are that these primary units are really describing, because that's what the units do. They describe the dimension. So the first one that we have is length. And I think most people know that length, the dimension length, in the SI system of units. Now, there's several systems of units. I'm going to be talking about the SI system of units. What does SI stand for? It stands for system or systeme. Actually, I'm sure that it's système in French. International. So the SI system, and so of course SI system of units is sort of redundant, but that's what it is. So the SI system of units is what we're going to be concentrating on today. Oh, I forgot to turn on my timer, didn't I? Just a second, there we go. Yeah, well, I'm a bit late, but whatever, we'll see how it goes. So the SI system of units is what we're looking at. There's also the British gravitational system of units. Foot, pound, BTU, all of those things. We're not going to be talking about those today. You're going to, as an American engineer, you're going to have to really know both of those two systems and be able to convert between both of those two systems, because both of the two systems are still being used in America today, right? Not really throughout the rest of the world. Australia, England, Europe has pretty much all gone over to the metric system. Most of the world has gone over to the metric system. England, actually, on their roadways, they're sort of like us. They still use miles. So anyway, let's get back to the SI system of units. So the length, as far as the primary units go, is just going to be a meter, right? I'll just write meter because I think everybody knows that M stands for meter, and when you're doing your homework, you're not going to be writing out meter anyway. So I think everybody knows that length is meters. Now, what is another primary unit, right? Probably the oldest one that we have is time, right? Time is the second. So length is in meters and time is in seconds. Another one is mass. I might talk a little bit about how these three are now linked together, and of course that is the kilogram. Now you're probably thinking, well, it's the gram. Why didn't they make it the gram? Uh, the prefixes for the various different things just wouldn't work out if they did. In fact, we had really two. The System International, if you look back at it, really had two different manifestations, two different flavors you would think of. We had the CGS system, and the CGS system stood for centimeter, gram, second. And that was sort of how it worked. But a centimeter is not a meter, is it? And then everything was based on the centimeter. That didn't work out well. So they went to the MKS system, which is the meter kilogram second system. And that's the system that we primarily use today. You can think of the difference between, in fact, if you read old books, and by old I mean 1940s, 1930s, 1950s, you're going to see that some of those old books still use a CGS SI dimensional system when they're writing in the book. Now, you can switch that to the MKS system. You can see here that this is 100 different than that, right? The second is the same in both. What is the second? What is the second? The second originally was a heartbeat. Right? The second is the only dimension and the only unit for that dimension that has stood the test of time. If you go back to 3000 BC, the second was still the primary unit of, because it was a heartbeat, right? Everybody had a heartbeat. You were carrying a heartbeat around with you. So if you've got a heartbeat, here's why the second has been around for so long. Let's say that I had a tree limb, right? And then I put a pendulum. Now, it doesn't matter what size rock you have at the end of that pendulum, does it? Right? Because obviously the momentum and the inertia, balance each other out. Potential energy to kinetic energy. I'm not going to get into all of that. Later on, I'm actually going to, work with potential and kinetic energy to show that they're all energy and they're all going to have the same combination of primary units that describe that energy. But right now, I'm just talking about the second. So it doesn't matter what size rock you have. You tie a string, right, around that rock, and you hang it from a limb of a tree. Now, if you actually take a heartbeat and you were to push that out so that it goes out to its maximum, and then it comes back from that maximum in 1 second, right? One heartbeat equals 1 second. So if it goes and completes a full cycle in 1 second, right? 1 second equals the period. Then how long is the rope? Right? How long is that rope? And so the length of that rope is 96.3 centimeters. Right? 96.3 centimeters, which was a long cubit. That's right. So they used, in fact, what they did was they took this second. So the second then defines the length in our gravitational system. And everybody that was living in Mesopotamia at the time lived on the surface of the earth. right? It wouldn't have worked for aliens coming from another planet or living on their planet. But everybody at the surface of the Earth, if in one heartbeat it goes out and comes back, it's going to be 96.3 centimeters. Now, what they did is they divided that by 4, and they made a cube, right? So they made a cube. I guess that's not really a cube, but you know what I mean. So they made a cube, and each side of the cube was L over 4, right? And then they filled it with barley, right? So we've got some barley in there. They filled it with barley, and that was their unit of mass. Now, isn't that interesting that the ancient Sumerians, 3000 BC, had linked their units of time with their unit of length with their unit of mass? We did not do that until the last century. We have not gotten back to where they were 3,000 years ago until the last century. So it's interesting, isn't it? It's almost like we had somebody went back in time and said, hey, why don't we do this to these guys? Oh, hey, that's a great idea. Not only that, they invented the sail, they invented the wheel, they invented writing, they invented irrigation. So the ancient Sumerians, we don't know where they came from. We think they came from like southern Iran, but they're not really sure. They weren't Semites like Arab and Israeli people. Um, so anyway, that's just something that you can, something interesting going back to the second. The second by far is the oldest, and of course, because it's a heartbeat. They wanted to change the length of the second when they came up with this, but the Swiss clockmakers who were involved in the System International development said, "Oh no, 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 no! That would be something against Switzerland." So they ended up keeping the second still, which is, like I say, the heartbeat. Now, there's 2 reasons that our heart beats about 70 times per minute rather than 60 times per minute. And that's because our metabolism has sped up over a 5,000-year period. And also, I think the second back then was probably a little bit different than it is now. Anyway, but it's pretty darn close. They probably did it more when they were, resting. I don't know. I don't know all of the specifics as to how they went through this, and it leaves a lot to be desired in standardization of weights, doesn't it? Later on, they did standardize weights and coins. That's only 3. That's only 3 of the 6 primary dimensions and units. So let's go on to 4, right? Now, you might say, well, those are the mechanical. I would say that length, time, and mass, and you can see we named it CGS, MKS, are really the mechanical units, the mechanical dimensions. Now what we want to do, because we're electrical engineers, is we want to get into the dimensions, the primary dimensions that are really related to electricity. And you might think that, a charge would be the primary dimension. But that is not the case at all. No, instead, because they didn't understand what charge was when they were making this up. I believe that if they really did understand charge and current at the time, they would have made charge the primary unit, but instead they didn't. They made current the primary unit, right? And current is an ampere. I might write that out, but I think everybody knows. And we shorten that to amp when we're talking about current. So current is the ampere, and now we've got 2 more. And what are those? What other primary units would we have that we would want to stick in there that we're going to be using in everything? Temperature, right? So far in all of the primary units we have, we don't really have anything that takes into account heat energy and heat content, do we? So what we want is we want temperature to be in the primary units as well. Now, you might say, well, okay, that's got to be degrees Fahrenheit. No, that's the British gravitational system that uses degrees Fahrenheit. We actually use degrees Kelvin. And I know the purists out there are saying right now, no, they're not called degrees Kelvin. They're really called kelvins. And we got rid of the degree entirely when we came up with kelvins. You know, I can't do that. To me, it's degrees Celsius, degrees Fahrenheit, degrees Rankine, and degrees Kelvin. You know, I just try to I just do that because that's what it is. You know, when we get to this point, what I like to do is I like to sort of look at the relationship between the four primary different, and this extends, yes, into the British gravitational system, but let's just see how all of these things are equated. Let's look at the boiling temperature, right? So if we've got the boiling temperature, what is that in Fahrenheit? I think everybody knows that that's 212 degrees Fahrenheit. What would that be in Celsius? Well, I think everybody knows that that would be 100 degrees Celsius, right? What would it be in Kelvin? Well, we know that Kelvin and Celsius are just displaced from one another by 273.15 degrees, right? We know the relationship between Kelvin and Celsius. Degrees Kelvin equals degrees Celsius plus 100. 100, that's not what I said. Plus, I was getting ahead of myself. Plus 273.15 degrees, right? So 273.15 degrees plus 100 degrees Celsius gives us 373. I'm not going to put the 15 in there. Degrees Kelvin. All right. Now, I also think that what we should do is probably put the Rankine degrees in there too. And so you're probably thinking, God, Rankine, I don't know Rankine that well. I've heard it before, but I don't really know what Rankine is like. Rankine is the same as Kelvin. So Rankine is to Fahrenheit what Kelvin is to Celsius. Does everyone see what I mean? Rankine is to Fahrenheit what Kelvin is to Celsius. So we've got 212 degrees right there. The difference between absolute zero and 0 degrees Fahrenheit is 456 degrees, right? 456. I'm rounding that a little bit, but you know, I probably should check that to be absolutely. I'm going to go with 456. And that would give us 668 degrees Rankine. Actually, I think it's, you know, I better check that. Just a second, let me check that. I'm going to come back and say, oh my God, no, it's 560 or something. I'm just thinking off the top of my head. Just a second. Okay, I'm back. Yeah, I was 4 off actually. It was 460. So I'll put that down here. Degrees Rankine equals 460 degrees Fahrenheit plus whatever the degree Fahrenheit is, right? So this would actually be 672, right? Yeah, don't, that doesn't have anything to do with that. So there you go, 672 degrees Rankine equals 212 degrees Fahrenheit. Now you've got to remember also that where these start is not the same. Where Fahrenheit starts and where Celsius starts are not the same. So what I want to do is I want to sort of look at these. There's boiling of water, right? Boiling of H2O. And then how about the freezing temperature of water? Let's shoot that across there. So for Fahrenheit, the freezing temperature of water is going to be 32 degrees Fahrenheit. Does everyone see that? And since we know it's 460 degrees, if we wanted to find out the degrees Rankine from the degrees Fahrenheit, it would just be 492. So we can do that, 492 degrees Rankine, right? Does everyone see that? Now, how about for the freezing temperature of Celsius is 0 degrees Celsius. And of course, that would mean the 273.15 or the 273 degrees Kelvin. If I took this all the way down to absolute 0, so absolute 0, of course, is where we take all of the energy away from anything that we have. Even, I mean, I wouldn't say that liquid hydrogen is liquid at absolute 0 because you can't really get down to absolute 0, but it's sort of a nebulous fluid, I guess you'd call that at that time, a super fluid. Now, at absolute 0, we see that we've got 0 degrees Kelvin and we've got 0 degrees Rankine, right? We have minus 273 degrees Celsius. And what do we have here? Right, it's not, that's 32 degrees Fahrenheit. And so this would be minus 460 degrees Fahrenheit, right? Because I think everybody can see that. So at 3 different points, and showing you the interrelationship between all 4 of the different temperature scales that you may be coming in contact with throughout your engineering career. And I know what you're saying. What's number 6? Oh my God, we've covered distance, we've covered time, we've covered mass, current, temperature. And in just using these 6 primary units. Now the last one is luminous intensity. Now you might say, well, why didn't they use luminous flux instead of luminous intensity? I wasn't in that group at the thing that was making the decision, so I can't really tell you. A lot of people think that they did use luminous flux rather than luminous intensity, but they didn't. When are you going to see this? You know, when you start to look at fiber optics, if you get a course in that your junior or senior year or something, you would start to get into luminous intensity. When you start to look at lasers and other types of optical and optronic products, you're getting into luminous intensity. So luminous intensity, I'm just going to give you this one. It's the candela. So those are our 6 primary units. I'm just going to bring that across there. Those are the 6 primary units, and I wanted to give you sort of a background in each of those, and of course to look at what the ancient Sumerians had done and what we've done. It's fantastic to study how dimensions and units and how we've used these have changed over time. Great, history lesson if nothing else, and to really see how people have grappled with this and how, we're very much the same as we were 5,000 years ago. Now, what I want to do is I want to look at some what I call derived units. And for some of these derived units, by the way, we have nicknames. We have nicknames. You, as engineers, should try to only use those nicknames once you've mastered the combination of primary units that describe that dimension. Okay? That's what I want you to do. So let's get back to this. So the first of the derived units, in fact, I'll just write derived units right here. And we're going to start with a very easy one that you probably don't even think is a derived unit. I'm going to start with area. And for a dimension that we're going to be deriving, we really need an equation that would relate that dimension to the primary units that we have, or to derived units that we have derived previous to the unit that we're deriving, right? Using those combination of primary units and build on those. I'll give you an example. Let's say that we've got area, right? Well, what's the defining equation for area that would use any of the primary units here? Let's say that I've got area equals length times width, right? Well, that's an equation for area. How about pi r squared? Isn't that the area of a circle, right? Now, both of these, whether I'm multiplying meters times meters or meters and squaring meters, is really going to give us the same combination of primary units. It's going to give us meters squared, isn't it? Do we have a nickname? Meters squared is only 3 syllables. So meters squared didn't really warrant a nickname. I threw out Grinquist, but nobody bid at that one. Well, I have a house that's 6 Grinquists. No, 600 Grinquists. Anyway, no, so that didn't work out. How about volume? Now, do you see what we're doing here? We can still use volume. I can still use a combination of primary units because I could say length times width times height, right? Each of those is a meter. I could say that it's 4/3 pi r cubed, right? Because that's the volume of a sphere, right? But it would still come out to meters cubed. Meters cubed is, again, that's only 3 syllables, so we don't really need a nickname for the general public to use to understand the concept of the dimension that we've created called meters cubed that defines the dimension volume. We don't. Lay people, easily meters squared, meters cubed, no problem. We don't have to make up any type of thing for that. So how about velocity? Well, velocity, we've got v equals the distance traveled over the time it took to go that distance, right? In fact, I could write that in its differential form as ds over dt. Now, ds is a very short distance, isn't it? And dt is a very short time. So that would be meters per second. Meters per second. Well, meters, that's 2. Per, that's 3. Second is 2. That's 5. That's 5 syllables. Meters per second. Well, that still isn't enough syllables to get a nickname, is it? No, no, it's not. Okay, that's velocity. Well, what's acceleration? What is acceleration? Well, acceleration is the change in velocity over the change in time. Oh my God, the change in velocity, but velocity is the change in uh, distance over the change in time. So that would be the change in the change of distance over, right, the change in time. So change in this over the change in time. Now, let me just take another color pen here for a second. I hope this pen, oh, that might not be thick enough. Just a second. Let's get I got an orange one here. Now, first of all, what did I write down here? So first, I've got V, don't I? And I know that this is the change in V. Let's not even worry about the change in T yet, right? Let's not worry about the change in T, because I've got the change sign here and that went over here. Can everybody see that orange? So that change sign goes here. Now the next change sign that I've got here, that change sign came from here, didn't it? In fact, that is the delta S that's up here. And the delta T that's down here is this delta T, isn't it? Does everyone see what I've done so far? I've just taken delta, goes here. Delta S follows it. Delta T is on bottom, it goes here. So, so this part here is the delta that's there, and this V here is this part here, isn't it? Does everyone see that? But what else do I have underneath there? I have another delta T, don't I? So how would I write that in differential form? Pay attention to me right here, all of you that think that eventually you're going to go to grad school. Pay very close attention to me. All of you people here that think you're going to grad school. This would be d squared s over dt squared, wouldn't it? That's right. That's right. So that equals meters, because the s is in meters. The d is squared, not the s. And down here, the whole thing, dt, is all squared, isn't it? So it's meters per second squared. Understand that. That's going to come in so handy in graduate school. Now, I'm only going to do one more because I think I'm running out of time here, but let's do force, because this is the first derived unit where we're not going to be using primary units. In fact, what's my defining equation for force? Isn't it mass times acceleration? Mass times acceleration. I probably should pull that up a bit, or oh no, there you go. Yeah, whatever, it looks good. Okay, mass times acceleration. When we know what mass is, that is a primary unit. That's a kilogram, isn't it? But now we know, we have derived what acceleration is. That's mass over second squared. So that gives us a kilogram meter over second squared. And what do we call that? What is the nickname that we let normal population people use that can't understand really the understanding of a kilogram meter per second squared. That's squared, by the way, squared. And we do this for young children, high school students before they become engineers and everything else, and we call it a Newton. That is the dumbed down version of a kilogram meter per second squared. Remember who you're becoming. You're becoming engineers. You want to understand it in the base form, not in this nickname that we give it so that the general population can, you know, partake in technology. All right. My timer went off, and I had actually talked for about 5 minutes before that timer went off, and I have to keep it to a certain size. So this is probably about 40 minutes. We're going to take up from there on our dimensions and units for our second lecture in just a minute. Actually, as soon as you click on the next lecture, you'll see it. It's going to be about 5 minutes for me, though. Okay, see you there.